good 75% of what we're going to do today, but the practice part is the hardest part. So I want to spend a lot of time practicing with you today, but I also don't want to lose you. So you got to kind of let me know when you're like, okay, I've totally lost, you lost me, Miss Lou, I don't know where we are. But you're going to be talking in your groups a little bit too to help you with that. So this is what you have on your desk around you someplace. But I want to recap what we did last week, and we'll kind of talk through the beginning of the next part. So basic stoichiometry. The big question, the big idea for today is, how do I convert between different chemical species in a chemical reaction? So chemical species is like what? You know, we're talking about like animals and plants and bugs. No, we're talking about chemical compounds and chemical compounds. So if we're ever talking about trying to convert between something on the reactant side to something on the product side, or even between two reactants or between two products, you can go from anything to anything with our coefficients, and our coefficients are called mole ratios. So all of these little relationships that are established, 2 moles of A produces 5 moles of C, where are we getting these numbers from right here and here? Where are we getting those numbers from? 2 and 5, Rishi. So that chemical equation, but what part of it are we pulling? So, but what number do we call the number in front of the reactants products? Coefficients, right? So these are all just coefficients, right? So the coefficients are the only thing we have to really be concerned about. But you know us, we're not always just given this reaction, right? We have to predict our own reaction. So then we have to balance our own equation. So we have to kind of do the grunt work to get there, and then we can apply it. So what do coefficients of a balanced chemical equation actually represent? We did talk about this last week. What did we say, Cameron, last week? So if you had to kind of just tell me, what do you think that these coefficients represent about each other? Okay, great. So number of moles, and sometimes it's called number of molecules or number of atoms. You could really narrow it down to do a particle in particular, but moles overall is related to the atoms and particles, so we can kind of just talk about it in terms of moles. Okay, so we also did this question, I think Jillian did it for me last week, but as we're concerned about like 2 different species, all you do is you pull the chemical equation.
I'm sure.
Okay, you can walk that way next time, not right in front of me. All right, so in terms of the mole ratios are in terms of like the number of things we need to react in order to produce something else. So, who's ever made cupcakes or cake? Okay, Chloe, tell me how you make it.
I either have the cake mix.
Okay. So let's just say 1 box of cake mix. Okay.
And eggs.
Okay, so maybe 2 eggs, a cup of water. So 1 cake mix box plus 2 eggs plus 1 cup of water yields 1 delicious set of cupcakes, or 12 cupcakes. I'm going to do it like that, say it doesn't. So these numbers we're saying are just a recipe to make something in particular. So we have to use something to produce something. So how does that make sense so far? We're kind of like idea of what we're talking about, chemical reactions in terms of like a recipe. Yes? No? Talk to me. Okay, some? Sarah, yes. Okay, let me jump off this for a second, then let's talk about what we know. Because we already know a couple of things. So, I'll go with it. Yeah, I'll stick with it right here. So you guys remember our mole map? Yeah. And I have it in a different order than what we had previously. But we always had 1 mole, and that 1 mole could be converted to 3 different things: particles, mass, or volume. Avogadro's number is what? 6102 times 10 to the 23rd. Does this number refer to particles or refer to the moles? It refers to the particles in 1 mole. Do not put anything other than 1 mole, people. 1 mole, unless it's a coefficient thing we're dealing with. So the Avogadro's number is referring to the number of particles in 1 mole. Molar mass, where do I get that information from? Periodic table. Thank you. I love it. It's being vocal here. Okay. So you're going to pull it from the periodic table. It's going to differ every single time depending on your plot count. And then 22.4 liters is only referring to volume of a gas at STP. And that 22.4 liters, is that going to go with the gas or with the mole? With the gas, with the volume, not the mole. The mole gets 1. So do you remember this a little bit from a couple weeks ago? Yeah? Okay, we're going to do this. We're going to do it bigger and better now, because we're going to put this in reference to a reaction. So I have a delicious reaction for you. I'm fond of cupcakes. I used to work in a bakery when I was in high school. And in college for like a catering service, and they would like let me bake the cupcakes and the cookies, which was dangerous because I always had to make one extra one just in case. Gotta try that thing before you give it away to people. Okay, so if I wanted to make delicious fluffy cupcakes for you guys, here's my recipe. But not really just like the overall recipe, it's the thing that makes them fluffy. So I have this. Do you remember this? The name of this? Sodium bicarbonate. It decomposes to sodium oxide plus water plus CO2. Huh, where'd you see that at? Just recently.
Teachers pardon the interruption. Bus 117 just arrived on the campus. Please allow those students into your classroom. Thank
Where'd
you.
you see this at before? The decomposition from Friday's lab, right? The one where you have the test tube and you're decomposing it and it's making water vapor. We tested the carbon dioxide with a what? Flaming splint, and what happened to it? It went out. Okay, so that was just a test for carbon dioxide, but we actually want carbon dioxide to happen in baking because that's how we get that lift in the cupcake or in the cake or whatever pastry we're making. So cupcakes use baking soda to make them rise. Baking soda is sodium bicarbonate, by the way. It's harmless. The reaction that creates the small pockets of air in the cupcake that gives them their texture is this. Write your reaction down. And we're going to walk through some interesting examples through the concept of baking, and then we're going to use some that are already on the paper that you have from last week. I gave you this one last week. Make sure you have this out. We will use this eventually. We're going to use it this year. This is the paper that I gave you last on Friday. Alright, so baking soda decomposes to sodium oxide, water, and carbon dioxide. Is that balanced? As you're writing down your reaction, consider if it's balanced. No, okay, so our first step is we are going to write our reaction. And we're going to make a balanced chemical equation. BCE, balanced chemical equation. Rishi, how do I balance this? Okay, so it makes two sodiums, two hydrogens, two carbons. So what do I need over here? Two in front of the carbon dioxide. And how many oxygens total here? 6. 2 times 3 is 6. Plus 1, plus 1, plus 4. We're good. Okay, so we have 6 on this side now. So we had a 2, 1, 1, 2. All right, so when we go through a problem, you always want to look for the details that matter and identify them, like, am I relating, like, to what content or what, which chemical we're talking about. So I'm going to scroll up. I need to make a total of about 50 milliliters of carbon dioxide per cupcake. Okay, so that's something important. We're going to think about that in a second. To create just the right amount of lift. What mass of baking soda is required per cupcake to create this much gas at STP? Like, that was a paragraph of information, right? So that's where the word problems get kind of iffy. You're like, I don't know how to approach this. So let's pull the information that's pertinent out and then start from scratch. So I need to make a total of 50 milliliters of what? So CO2. So let's write it in the terms that our reaction is already written in. So I need to make about 50 milliliters of carbon dioxide per cupcake. And I'll just kind of put that right here, because that might be important for us. So this is going to make the perfect cupcake. So the question is, what mass of what? Okay, so what mass, but question, grams, because we're taking our words into usable terms, grams, of what's baking soda? NaHCO3, okay? So what mass of baking soda is required per cupcake? And that's just something that we might need to know. So that's per cupcake, and this was per cupcake. So we're just talking about per cupcake now. So we're kind of talking about the same terms. That makes sense. We're going to be referencing them together. So what mass of baking soda is required per cupcake to create this much gas at STP? What is it talking about, this much gas? Okay, well, I hear you going 22.4. That might be important later, but what gas is it speaking of? Carbon dioxide. Okay, so basically, what mass of baking soda is required to make 50 milliliters of carbon dioxide? That's really what the question's asking for. So we have already our given information. You can read all this. You see it's a lot of information, but it's really not. It's only this. 50 milliliters of carbon dioxide is what I have that I want to get to. But my question is, how much of this do I need to actually cause this decomposition to make this much gas? So this is my given, and this is my unknown, or this is my question. Whenever you start a problem, what do you always start with? With the given. Okay, Ignore what it's referring to right now. Let's just start with our basic information of the given and think about what we know that actually relates to that so we can move from step to step to step to step. There might be 6 steps in this question, and that's okay because you know your simple relationships. You can go from there. All right, so write down 50 milliliters of CO2, and you're going to put your multiplication mark in it and a fraction. And your job right now is to think, I know there's only 3 relationships. 1 mole can be related to particles, mass, and volume. But sometimes within that, you can't just go straight to volume. You might have to get from milliliters to liters first. So let's do that first, because I know that in the end, between volume and moles, that's going to be where I'm going to have to go, because that's the only thing that volume is related to. All right, so what's the conversion from milliliters to liters? 1,000 what? Right, so 1,000 milliliters is going to go on bottom, and that's milliliters of CO2. Write your identities. It's very, very important to write that, because we're going to start talking about apples and oranges here soon. The 2 different compounds we're talking about are CO2 and sodium bicarbonate. All right, so milliliters of CO2 to 1 liter of CO2. Okay, so I've successfully converted small volume to a larger volume. So milliliters and milliliters cancel. Now I'm in 1 liter of CO2. Still, because I have this reaction up here, and I don't know who just told me, I think Cameron told me that these coefficients 2, 1, 1, and 2, those were called, those coefficients refer to what? Number of moles. So we can actually call this like 2 moles of sodium bicarbonate to every 2 moles of CO2, because what you're referencing in this problem are these 2 individual chemicals. So I'm not able to really relate these yet, because these are moles and I'm still in liters. So what do I need to do next? Convert to what? Well, I'm in liters. I need to convert liters to moles. Okay, so let's do our next step here. I know liters have to go away, so they have to go where on the fraction? On the bottom. So that's, thank you, 22.4 liters is equivalent to 1 mole. And that's information that you knew from about 2 weeks ago. That's what this conversion is right here. Okay, so now we're at the magical point that we did not know even existed yet. We are now able to go from moles of something to moles of something else. So for example, from moles of carbon dioxide to moles of sodium bicarbonate, because the question is not about carbon dioxide, right? It's about sodium bicarbonate. So we need to find a way to bridge that gap. Well, that gap is bridged by these mole ratios, which are actually the coefficients. So on your map now, we actually have another branch. We can go from 1 mole, and I won't even put the ones there anymore, I'll just put mole, number of moles, and number of moles. We can go from particles, mass, or volume to the mole that we know, and then we can go from moles of A to moles of B, or whatever compounds we're talking about, through the balanced chemical equation. That's the step that we didn't know yet. So now we do. So in terms of the ratio, we have 2 to 2. So I'm going to actually write the ratio with their individual components attached to it like an identity. So the 2 moles of CO2 go on bottom. Why am I putting that on the bottom? Right, because this mole of CO2 and this mole of CO2 needs to cancel. And I'm going to cancel as I go. Liters of CO2 canceled with liters of CO2. Moles of CO2 cancel with, oh, I haven't actually written that all the way yet. Let's write that all the way. So 2 moles of CO2 came from up here. And now I need to relate that to the sodium bicarbonate. I'm actually going to put 2 moles of sodium bicarbonate on top. Does everybody understand where I'm getting this step from? Nick, where am I getting this step from?
I'm getting it from the amount of moles in the balance equation.
Right, so the balanced chemical equation is the only way I can get that step. So I have to have a balanced equation to even start this. 1 second. Okay, so moles of CO2 cancel, moles of CO2 cancel. So let's kind of refresh our brain. What was the question here? What am I looking for in the end? Grams of sodium bicarbonate. Nobody even went back through and read that, right? Because we have this written down. Okay, so am I close to the grams of sodium bicarbonate? Yes, what's my last step? Go from moles of sodium bicarbonate to grams of sodium bicarbonate. So I'm going to write that down here. So what am I looking at for this information? Periodic table. So 1, and this is the point that most people mess up on. You see this 2 moles of sodium bicarbonate? You guys want to put 2 down here. Do not put 2 down there, because you know that if we're going from mass to moles, it's always that 1 mole that we had there previously. Stick with the 1 mole because the 2 has already been accounted for through our ratios. So 1 mole of sodium bicarbonate weighs, anybody? Add that up for me. 23, 24, 6, 36. What's 36 plus 48? 84?
Yeah.
Is that 84? Okay. Okay. And that is our final destination. Moles of NaHCO3 and moles of NaHCO3 cancel. And we have the only unit left, which is grams of sodium bicarbonate. That's the unit we didn't cancel, and that's the unit we wanted, so we know we're in a good place. Yeah? And then we need to calculate. Question.
Where you like use the
Sig figs? Yes, always. All right, so in your calculator, I want you guys, if you don't have a calculator, Maddie, can you bring the whole tote over this way? If you don't have a calculator, raise your hand. Because I do want everybody calculating with me today, make sure we're good. So, Maddie's walking around with that. Maddie's so nicely going to be volunteering to walk around, and everyone else should be calculating. And if you would like to, just multiply all the way across all your numerators, and then separately divide by whatever your denominators equal, that's fine. Or in your calculator, you can do 50 divided by 1,000. So everything in the denominator gets divided by 50 divided by 1,000. And since you're still multiplying by 1, it doesn't matter. You can divide by 22.4. And then again, this is a multiplier. So on top, you multiply by 2, the bottom, you divide by 2. But that's just the same thing. So that's 1 actually. And then times by 84. Anybody got an answer for me? Say it again. 0.1875. What are the units? Grams of sodium bicarbonate. So I'm writing the full thing, and then I'm going to round it just so that we don't get confused where I'm rounding at. So in terms of sig figs, the question started me off with 50. Where did 50 go? 50. And just for clarification purposes, I'm going to put 50 points so that there's 2 sig figs there. There's 3 sig figs here. And these ratios are not true measurements. Do not count them into your sig figs. So the only 2 things that I really see that contain sig figs are this. There's 2 sig figs here. This is a constant. This is a constant, but it could have been like 84.0000, depending on what the sig figs we used in our calculation there. So this is a constant at 3 sig figs. This is going to have an infinity number of sig figs because it's just a masses from a periodic table. So the 2 sig figs should be our lowest one. So this needs to be rounded to what? 0.19. Yeah, the 7 rounds the 8 up, so that's going to be 0.19 grams of sodium bicarbonate. Okay, do me a favor, let me pause for a moment. On the paper that you had from Friday, pull this out. And I want you guys to look and see what we just did and follow this new mole map that has an expanded version to it. So you can kind of walk through your step-by-step process. So where do we start on this mole map? Look on your, you guys have everybody has this in front of them? No, you should find it in the notes that you had from Friday. I passed it to you Friday because you had some things that are actually due Wednesday. All right, so on this mole map, we started at molar volume. You see molar volume at the top? I actually have this on my screen, so let me scroll to it. So here it is. All right, so where do we start here? Volume in milliliters, right? But we converted to liters first. So we went from volume in milliliters to liters, and then we did what? We went to moles and we went to CO2, but we used 22.4 here, liters per mole. And then this was our stuff that we did way back. Now we're here, we went from moles of CO2 to moles of sodium bicarbonate by using the mole ratio from the balanced chemical equation. Where is the mole ratio coming from, though, in that balanced chemical equation? Where do I pull the numbers? Coefficients. Okay. Then we went from moles of our sodium bicarbonate to what? We went to grams, which was using the molar mass, which was straight from the periodic table we had to calculate. Okay. So from this, what's new really for us? That connection, right? That's it. So I want to make that clear. Like, you already know half the battle, guys, but we have to learn how to apply it now. So I'm gonna pause for a moment, and you guys tell me from oh my lord, here we go. Okay, from this next step, talk in your groups how you would address that one. From this next one, if I want to make 3 dozen cupcakes for my favorite chemistry class, what total amount of baking soda would I need? Multiply what by? I hear you. All right, so is this like really a math question or a chemistry question? It's more just math, right? You're just like, oh, okay, I have that 0.9 or 1.9 grams of baking soda, and what are you doing to it? Why are you multiplying it by 36 versus 3? Okay, so this was grams per what? This was per 1 cupcake. You guys wrote that down, right? Per 1 cupcake. So what you can then say down here is, this is how many grams per 1 cupcake. And if I now have, how many cupcakes do I need? 36 cupcakes. I'm going to multiply this by 36, but not only 36 cupcakes, 36, but 36 cupcakes. So then what unit cancels? Cupcake, yeah? And I do 0.19 times 36. What is that, by the way? 6.85. And that's 8.4. I'm just going to say 8.4, and then we're going to round in a second. So I need a total of this many grams of sodium bicarbonate to make enough cupcakes for this class, right? So that wasn't really a stoichiometry problem, but you can apply the units and make it make sense through stoichiometry, which is your unit cancelization process. So I would actually mass out that much to begin with to make my cupcakes overall. So that was not really a true chemistry question, but it's related to what we've been doing. All right, keep going. Using that mass, so that mass right there of baking soda, how much total sodium oxide would be produced? So let's start with that. Work with your groups on that one. Talk about what you should do first and then do it. Write down your given and your unknown and see if you can connect the dots between them. All right, raise your hand if you feel like you have a shot at this. You maybe got a gut reaction. Roddy. Before you tell me, actually, can you tell me what my unknown is?
Your unknown is sodium oxide.
But when you say sodium oxide, are you talking about liters, grams, moles, particles? What are you talking about?
Grams.
Grams. This is how much. That's probably referring to grams, right? Much is grams, so that's grams of sodium oxide. Okay, so your given is the 6.84 that we just got. We're going to sodium oxide. What do you want to do?
You could start out on the mass, like the moles map.
Okay, so let me scroll to my mole map because you're pointing to it, and I want everybody to see what you're pointing at. Okay, oops, sorry. Okay, here we are. You want to start out with grams, right, of your sodium bicarbonate, and then do what?
And then go to the moles X.
Okay, so that moles is of our sodium bicarbonate, right? So we're using its molar mass there, and then what?
And then go to moles Y by doing the molar ratio, which would be
I think it was 2.
2.
So yeah, 1/2 because the sodium oxide had a 1. You guys have your balanced chemical equation in front of you. I don't. I'm doing it from memory. Thanks, Robbie. So you went from moles to moles using your coefficients, and then what?
And then like to the molar mass.
Using the molar mass go to grams. Okay, good. So do you need this mole map to figure that out, or can you think about what you already know and apply only this one extra rule? Who feels right now that you need the mole map just right now? So we just kind of started. Okay, I was hoping most of you would use it first, and you start to learn that you actually don't need it because you actually know everything from past. I give you a lot of credit, you know that, but I understand we're still working on it. Okay, so finally, I'm back to my my question here. So Robbie's saying start with your 6.84 grams of sodium bicarbonate. Labeling these babies are super important because at this point, if you put grams, you're like, grams of what? What are we talking about? So, and then he said use molar mass. Well, what do I put on top? 1 mole of thank you, sodium bicarbonate, because you can't just leave it hanging. And that I think we said was 84 grams by adding up the molar masses, or the individual masses. So then our grams of sodium bicarbonate and our grams of sodium bicarbonate can cancel. Now I went from mass to moles. Now I'm at moles of one thing. I gotta go to moles of the other thing by using what? Anybody? Mole ratio, and that's where you guys have your, mine's way up here. This is a 2-to-1 ratio, but because I'm going to the sodium oxide, that has to go on top. This has to go on bottom because I have to cancel this. So 1 to 2 is what it looks like here. So I'm going to put 1 mole of sodium oxide is related to 2 moles of sodium bicarbonate. And I got this from my balanced chemical equation. Don't forget that step. And so in that case, that simply just is allowing me to cancel my moles of sodium bicarbonate, my moles of sodium bicarbonate. Now I'm in moles of sodium oxide. And again, my last step was to just answer my question, which was grams. So what do you call my last step here? Molar mass conversion, right? So because I'm going to mass has to go on top. So grams of sodium oxide have to go on top. And my 1 mole of sodium oxide, which I know the relationship between these is 1 mole is equal to its mass from the periodic table. 46, what's 46 plus 12? 58? So 58 grams? Okay. I'm just doing approximate, sorry, from my head here. So that should be 58 grams based on periodic table masses. And after this, yeah. Thanks. Oh, I said plus 12, plus 16. Say again, 61.98 grams. Okay, and then from there, what do you have to do? Calculate by doing 6.84 divided by 84 divided by 2 times 61 point blah blah blah. And anybody have an answer for me? 2.5 what? Okay, I'm gonna stop there. Grams of sodium oxide. Okay, so that basically means this cupcake that we have, these 36 cupcakes we've created, have a total of 2.52 grams of sodium oxide in them. So that's a total, right? So what would I do if I wanted to figure out how much was in each cupcake? Say again? Ooh, I could, but that would take me a lot longer than I have to do it. So this is how much I have in 36 cupcakes. So how would I find out how much is in each cupcake with one step? Divide this by 36. So divide that by 36, how much you get? Points. So that is what again? Something like that. That's what we divide by 36, and we got this. So why would this be important in the real world, right? So in this case, what we had to do was we had to like double check how much of each reagent or each product was made in a cupcake, because some of these things are toxic in large quantities, right? We didn't want to kill our customers. We wanted them coming back for more. So if whatever we made decomposed to form a ton of sodium oxide, we were doing it wrong. Because if there was in the end too much sodium oxide in the end, it makes it taste really bitter, and it's also a little bit, it's not lethal, but it's having too much of anything is a bad thing. So you always have to double check your quantities, make sure that you didn't have too much in a particular product, because we wanted our customers to have a good experience with our cupcake. So my boss lady, she was the head chef, head culinary artist. She was a chemistry major, because all baking is just chemistry. Isn't that kind of crazy? There's like a lot of food science going on out there. And there's a flavor chemist at S&D Coffee. You guys know where S&D Coffee is? It's towards like the other side of Concord, towards Union Street. S&D Coffee is a big Concord coffee company, but they make they're trying to get into like the Starbucks business for like frappes and different types of like cool drinks. And they have a flavor chemist on staff, and she just plays with chemistry, and she makes different flavors, and she puts them into the coffee, and then she makes sure that they stay around for a long time and they don't decompose to like toxic things. So if you like food and you like chemistry, food chemistry for you, okay? So let me pause from here And let's see where we are in terms of mole ratios. Because, I think we're good to go here. Here. You guys tell me, what is the mole ratio between iron and calcium permanganate? What's the mole ratio? Iron and calcium permanganate. 2 to 3. So all you're doing is looking for the names, and you look at their coefficients, and those are called the mole ratio. What about the mole ratio between iron 3 permanganate and calcium permanganate? 2 to 3 again. 2 to 3, based on what we're talking about. So remember, mole ratios are just pulling the contents from the coefficients, and that's it. Give me a thumbs up if that makes sense. Because that is the only new thing. It's just we're applying it now in a big picture. So I'm going to kind of take our time as we go through the first couple of examples, just to make sure I'm not losing, okay? So I want you guys to do the reaction first. Step 1 is always have a balanced chemical equation. I didn't write this all the way earlier. Balanced chemical equation. Step 2 is, and as I was modeling this for you as we are going, you're going to write down your givens and your unknowns. And then step 3, you can use your mole map for now, but towards the end, we're going to try to wean ourselves off of that. So, using that logic, the very first thing is balanced chemical equation. Write down the synthesis of aluminum oxide from its elements. So I'll give you a second to start that first. And when it says synthesis of aluminum oxide, it means you're producing aluminum oxide. That is on the right-hand side of the arrow. Help each other out too if you forget that you're crisscrossing charges. All right, so with the synthesis of aluminum oxide, what is aluminum oxide, Lindsay, up here? Wonderful. So she crisscrossed charges and she got aluminum oxide. So what are the elements? Blank and blank. What are they? Aluminum and how do you write oxygen? Diatomic. Thank you. Okay. So then as you balance this, what do you need to have in the front of aluminum? 4 actually. I'll get there in a second. But the reason was because the 2 and the 3 of oxygens cannot be balanced just by themselves. So you have to kind of do the least common multiple. So they have 3 there and a 2 there. That's 6 oxygens, 6 oxygens. 4 aluminum, so you need 4 aluminums. Okay, so let's name off the mole ratios, and I'll write them down as you go. Pretty, tell me one mole ratio. Pick any of them that you want. Okay, so there's 3 moles, right? That 3 is the talking about oxygen. 3 moles of oxygen, that's equivalent or related to 4 moles of aluminum. That's one relationship, or I could flip this. I could write it either way. It's just a relationship. Kyle, give me another one.
4 moles of
2 moles of aluminum oxide. Beautiful. And I could write that again either way. You could relate them either way. And then Caleb, give me one more.
3, 4.
Uh-huh. Beautiful. So you can take any combination of them and you can write it top and bottom or flip them. It depends on the necessity in terms of what the reaction or what the question's asking for. So mole ratios are not too bad. All right, now let's put this in context. We have our balanced chemical equation. We need to write down our givens and our unknowns. So question, and write this down with me, I promise it'll help you in the end. How many moles of aluminum are needed to form 2.3 moles of aluminum oxide? All right, so I have my given and I have my question. What do I have to start with? Kim, what do I have to start with? Okay, so if you have your mole map in front of you, you can help yourself. But you're telling me I need to connect this to see what it connects to, right? So I need to take my moles. So my 2.3 moles of aluminum oxide. But we're already at moles, right? So I'm not, usually I start at the top with grams or liters or something else. I get 2 moles, but I'm already to moles. So if I'm already to moles, I just have to go jump 1 step from moles of aluminum oxide to moles of aluminum. Yes? Using the mole ratio, which I already have up here, right? Which one is the right one? This one? So I'm going to take this. Do I write it as is or do I flip it? Why as is? Because my moles of aluminum oxide are in the correct place, right? So I'm going to put 4 moles of aluminum on top and 2 moles of aluminum oxide on the bottom, and that's going to allow for my aluminum oxide to cancel. Moles of aluminum oxide, and then 2.3 times 4 over 2, so that's basically times 2, so that should be 4.6 moles of aluminum. Because the only unit I have left is moles of aluminum. Give me a thumbs up if that one made sense. We just simply used a mole ratio from beginning to end because they were asking both for moles. Okay, I'm gonna scroll up a little bit here. All right, so you guys start the next one at your table. Do this one in your table group. Talk and write down every step, including your question and given. FYI, these questions are on the little sheet that I was referencing with the mole map on it. We're doing the lectures 1 through 3. It's right to the right of the little map itself. So I'm sure we got here. That's the easy part, is setting up your question and your given. So this was, I just had this conversation with somebody. The only relationship that happens within, between 2 different things, like aluminum and oxygen, there is only one relationship between them. It's the reaction. The reaction has the magical coefficients that gives them the appropriate relationship. Like, I can't make 15 cakes from 1 cake box, right? That would be awesome. But I can't make 15 cakes, I have 1 cake box. So the relationship is the reaction. You have to reference the reaction for the mole-to-mole relationship. So, Margaret, what is the relationship between aluminum and oxygen? 3 moles of oxygen for every 4 moles of aluminum. So I have to go to the balanced chemical equation for this step. Because if I'm already to moles, I'm halfway there, right? I'm in the middle of the map. Okay, so then if I'm in moles of aluminum, and now I'm out of moles of aluminum, I'm now in moles of oxygen. My final destination is liters of oxygen. Is there a relationship between moles and liters of oxygen? Yes, what is it? 22.4. That's the step that we kind of knew in the past. So 1 mole of oxygen has 22.4 liters in it. And so at this point, I'm done because my moles of oxygen cancel. I'm in liters of oxygen, so then I'm able to stop and calculate. So stop and calculate, what do you guys get? 14.112 is what I've heard, and that needs to be rounded to correct sig figs, and my sig figs here are in the beginning of 2 sig figs, so what would I convert to? Just straight 14. So 14 liters of oxygen. give me a thumbs up if I'm good to move on here. I'm trying to at least do a sample of different types of questions for you. So that was number 1. You guys look at number 2 on your sheet. I'm going to leave this here for just a moment. Write down the reaction first. Which one? It's called lecture problems. Okay, just do number 1. Okay, example 2. So I was starting off with some easy ones, then we're going to move to harder ones. So you see combustion of propane gas. You need your organic sheet. What's your organic sheet? Hold on. That's just so you don't have to look at the board all the time. I put them so you can have it for home. Lael, do you have a propane gas for me? C3H. What I'm asking Lael, did you say?
Yes. C3H.
That's it, right? So you do 2N plus 2, that's how you get to hydrogens. So 3 carbons, if this is an ane. Prop means 3 carbons, and then the ane ending means 2N plus 2, so that's 2 times 3, so this number of carbons plus 2 gives me 8. So you can figure it out from your brain or from your chart. All right, so propane is combusted. What's that mean, reacts with Trini? Oxygen gas, right, O2 gas. Okay, what do all combustions of hydrocarbons make, Miles? Hydrocarbons combust to make 2 things. H2O and carbon dioxide, right? Wonderful. Okay, balance that out first, and then I want you to start with your givens on your next step, or your question on your givens. If you're good to proceed, go ahead and proceed. Help the neighbor out. All right, on A, raise your hand if you feel confident you can do the first step. I got a couple people. Well, the first step, well, we already done, right? The balanced chemical equation and then writing down the givens and the question. So you have to start with your given, right? So you start by writing 13 grams of propane. Guys, there's only one thing you can do with grams. You absolutely have to convert to what? Moles. And that's right here, right? This is not new. You have mass, you have one connection, it's to moles. You have to convert to moles. So from your periodic table, you found the molar mass of propane to be 1 mole of propane weighs, anybody? 40, is it 44? 44.097 grams of propane. So the very first step was old school. You take your grams to moles, you're done. Now we're in moles of propane. Nobody cares about propane. What are we looking for? We're looking for oxygen. So we don't care about propane. We care about oxygen. The relationship between propane and oxygen is what? Where is it at on my board? The relationship between between oxygen and propane. Where is it out on the board? The coefficients from balanced chemical equation. This is your story. You have to follow your story. It's about this reaction. So your grams of propane have canceled. Your moles of propane need to go on bottom, and that's a big 1 right here. Even if it's not there, you should see it's a 1. 1 mole of propane is related to oxygen in a 5-to-1 ratio. So 5 moles of oxygen react with 1 mole of propane. So this is from your balanced chemical equation. Okay, so now we're like, yeah, we're in moles of oxygen, right? But the question wasn't moles of oxygen, it was grams of oxygen. So what's our last step? Shout it out. Convert what? Moles to grams. So you still only use, just like we used to, 1 mole of oxygen. Its mass is oxygen plus oxygen, which is 16 plus 16, so 32 grams of oxygen per 1 mole of oxygen. So since our moles of propane cancel, top and bottom, moles of oxygen cancel, top and bottom, we're stuck with grams of oxygen, yay, which is our final end that we wanted to get anyhow. And so then as you calculate, anybody got the calculation for me? I'm gonna write that over here, 47.2 grams of oxygen, okay? So, is that the correct sig figs? Yes, because we start off with 3 sig figs, we're going to end with 3 sig figs here. Because somebody calculate for me. 13 divided by 44.097 times 5 times 32.
Let's get 5 there.
We used our mole ratio from our balanced chemical equation. 5-to-1 based on the 2 identities that we're talking about, which was propane and oxygen. Their only relationship exists in a coefficient form from the balanced chemical equation. So before I go any further, tell me 1 second.
That's wrong.
Wait 1 second. Is it wrong?
Yes.
What's wrong?
No, I think that equation is wrong.
I think the equation. Try again. Check on your paper because I'm pretty sure it's right. Okay, so we went from where were we at here to start with, guys, on that particular question? We were at grams, which was grams of propane, right? We went from mass to moles using the molar mass of propane, and then we went from propane to oxygen using the mole ratio, and went from oxygen to grams. Okay, so we've done grams quite a bit here, but there's many other things that could happen. So we went from grams to our moles to grams using the molar mass. So I'm going to teach you this one now. This is one we've not seen yet. Question. I did oxygen's molar mass, which is 16 from oxygen, 16 plus oxygen, 16 plus 16 is 32. Yep. So I'm going to teach you this one in just a second. Actually, let me finish this question before I move too much farther. Okay, so we made it through the big one. Let's keep going. You guys write down your question and your given. I'm giving you a chance to kind of get started without me first to see if you can springboard from the information given in the question. Help a neighbor out too if you can. Ignore the fact that it says excess, just says it reacts with oxygen. You're like, you knew that because oxygen's in the reaction. Scroll back up. You guys have this on your paper too, so scroll up a little bit. Oh, there you go, right there. That's right. I know this is the right one. I think I put acetylene. Is that what I put acetylene? I don't know what I was doing. I was thinking. I think I mixed up two questions. It's propane. That's why I tried to leave this up here for you now. On your sheet it says acetylene. I think I changed my gases between when I printed your sheet and mine. All right, so from your starting point, you start with your 0.5 moles of propane. What do you have to do next? You're at moles, and you're in moles of propane, but nobody cares about propane. What do we want to go to? We want to go to CO2, right? It says in excess oxygen. Ignore this whole little phrase, because I think right there, it's extra information. It's important, but it's extra information that you don't actually need. So, Margaret, what did you do next? No, hold on, sorry. Give me my step right here. So there's 3 moles of CO2. Where are you getting this number from? From the Bouncing equation, which is the relationship to every 1 mole of propane. Okay? And then, yes, go ahead and tell me what you did next.
And then I converted the moles of carbon dioxide.
And so where'd you put grams here?
On top.
CO2. So she went from, she said, I'm in moles. If I'm in moles of something and I want to get to moles of something else, there's one relationship there, and it's the Bouncing equation. So she used her mole ratios of 3 to 1 from the relationships we had in our reaction. And then moles of propane canceled. And then she said, okay, I'm in moles of carbon dioxide. My questions go to grams of carbon dioxide. And so the relationship between moles and grams is molar mass. Molar mass of carbon dioxide is about 44 grams. And moles of carbon dioxide cancel. Question, Lindsay? Ignore that because you've already utilized that ratio. You have used it, right? It's right here. Now you're just saying, oh, I've got 3 of them, great, yeah. But for every 1 mole of CO2, each of the CO2s weigh 44. If you did 3 of these, you'd have to have 3 times 44 on the top, whatever that is. So it still works down to the lowest ratio being 1 of these to its mass. So don't get crazy, don't use the ratio more than once. And then we're good. Anybody got the final for me? 66 grams of CO2. Is that good? Okay. All right, so that was a short one because we already started with moles. All right, you guys do the last one, and I'm gonna, sorry, not the last one. Do C for me, because I will have to go. We have about 25 minutes left. I can make a molarity one for you before you go. If you're feeling it, please help take off your table, because I'm making sure I get the main examples on each of you. able to move on part B, go ahead. Made it through part C. Double check that through your process, and let's just verbalize what we did here. If you're moving on to part D, because you got this under your belt, and move on. But we started with grams, and the only connection between grams in the world of chemistry is grams to moles. That is the one connection, grams to moles. So we had to use grams to moles using the molar mass of propane. So grams of propane cancel. And so now that we're in moles of propane, we're like, nobody cares about propane. You have to go to the thing that you desire, which was oxygen. And so we pulled from the balanced chemical equation the relationship between oxygen and propane, which was a ratio of 5 to 1 from the balanced chemical equation. 5 moles of oxygen for every 1 mole of propane combusted. That got me out of propane land into oxygen land. And so the last step was to get to gas in liters, and so the relationship between moles and liters is 22.4 liters per mole. Give me 2 thumbs up if you made it through those steps. All right, still got some people we're going to keep kind of wrapping up a couple more of these with. So if we got here, the moles of oxygen cancel. Liters of oxygen are the only thing remaining, and that's how I guide myself as I double check with my my unknown that I questioned to begin with. And so, so like 33 something. What's the final answer here? 33.0 liters of oxygen. If you calculate. I'm not going through calculations, I'm going through setups right now. All right. I'm going to let you guys set up the last one, and then we're going to go to our molarity. And again, please follow your mole map if you don't know the next step. Point where you are on the mole map, and then move to the following. Thank you for being patient. I'm trying to get a chance to talk to everybody before you guys leave, because it's kind of like a Friday, and I won't see you tomorrow. But it's not Friday, because I'll see you on Wednesday. Did somebody just say woohoo? Whoa. Hurts my feelings, guys. Hurts my feelings. All right, so you guys went from mass to what? Oh, sorry. My bad. Question, molecules of water. And that says molecules. Okay. And 10 grams of propane is what we're starting off with. Okay, grams of propane happens to be 44 grams again. It hasn't changed. We got some moles of propane, which is a big step for us in our relationship. Now we're going to relate propane to water. What's that mole ratio? Who gets the 4? Water, right? 4 moles of water to every 1 mole of propane combusted. And I'm putting propane on the bottom, so grams have canceled, moles have canceled. Now I'm in moles of water, and we're going to molecules of water. What's that relationship? Avogadro's number, which is old school, right? We know that. 1 mole of water contains 6.022 times 10 to the 23rd molecules of water. Okay, and then moles of water cancel, moles of water cancel. And whenever you get there is your calculated value. What is that, by the way? 5.6 times 10 to the 5.46 times 10 to the 23rd molecules of water. Whew. Okay, I'm trying not to kill a dead horse, but I don't think it's dead yet. Okay, I gotta do one more. So, in terms of following your mole map, please use that so you feel comfortable with it. But it's the only thing that's new is that relationship between moles and moles. The last thing on the mole map we haven't even touched yet is the very top left, which says molarity. Do you see that? Okay, this is the only new conversion that's kind of brand spanking new to everybody. And I'm going to show you what it looks like first before we move on, and then we'll actually do a problem with it. So in terms of this thing called molarity, you hear mole in it, right? Molarity. And so it says solution concentration molarity. Molarity's units are moles per liter. Now, I know you're like, oh, but we already have something for liters, right? But this is the difference between liters. This is liters of a gas. Please circle that, highlight that, write gas really big. If we are talking about gases, you use the 22.4 liters per mole. If we are using solutions, and what do I mean by solutions? When I say like solutions being mixed in water, what's the term for that? Aqueous. Okay, so it'll be an aqueous solution. If we're talking aqueous solution and it gives you volume, you shall not touch 22.4. Absolutely cannot. You have to use molarity, and they'll always tell you the molarities of the problem. Now, if molarity's units are number of moles per 1 liter, it'll give you things like, oh, I have a 0.2 molar solution. So molar is kind of how we refer to molarity. So if something's really, really, really concentrated, it's going to have like 20 moles per liter, per 1 liter. That's really concentrated, 20 moles per liter. But it also could be really, really dilute, whereas dilute might be, I don't know, 0.02 moles per liter. So it's just relatively talking about the concentration, like how much stuff's per liter in a solution. So the way that these are referred to is molar, but it's not written as molar, it's written as like 0.20 big M. Big M means molarity or molar. They all mean the same thing. So 0.02 big M means 0.20 moles per 1 liter. So if you ever see this, don't write it like this. Write it as a fraction, because then that makes more sense to you, because all we've been doing this whole time is using fractions, right? And canceling units, canceling units, canceling units. I'm going to show you how to implement this now. So we have this magical conversion, relationship between these and volume. So I'll keep writing that right here. If you ever have big M given to you, meaning molarity, and you multiply big M by the volume given to you, so I'm going to show that here and give myself some more space. So if I ever take 2.2 moles per liter, and I take my molarity and I multiply by liters, what cancels? Liters, so what I have left? Moles. And that's half the battle, right? You've already gotten to moles. Now you found another way to get to moles, which is getting you to here, right? It's getting you to your moles of blank, whatever you're talking about. So once you get to moles, you feel good to kind of go further, moles to moles, and then moles to anything else. So it's just this one new thing with solutions. You'll do molarity times volume in liters to give yourself moles, and that gets you to here. And then from there, you can move to wherever you got to go. All right, so let's do an example with that using a reaction that gives us solutions. Okay, consider the single replacement reaction between magnesium and copper 1 chloride. Write down your reaction first. Write down your reaction first. I do have about 5 minutes left, so I'm going to do only A for you right now. So we got a 45, we got a 37. So magnesium copper 1 chloride is CuCl because there's a 1 and 1 crisscross. What kind of reaction is this? Zinc replacement. Who replaces who? Magnesium replaces copper. So copper gets booted to the cold, and magnesium pairs with who? Chloride, but what's the formula? MgCl2, because 2 from magnesium, 1 from chlorine gets crisscrossed. Okay, so you're assuming that this is solid because it's just a simple metal. This is aqueous because I'm going to tell you later on, you can see it down here, it says it's a solution. Copper is a solid, and then this is probably aqueous too, but we really don't care. But we're going to put a 2 here to balance, and a 2 here to balance, and I think we're good. So writing the reactions old school, we can write reactions, we can predict our products. Now, this is where the givens get a little bit jumbled. If a 500 milliliter of a 0.4 molar solution of copper 1 chloride, whoa, that's a lot of information. But I just told you guys that you could take your molarity times your volume, and you get what? Moles. Before I even finish reading the question, let's write that down. Molarity times volume gives me moles. Now, my molarity is 0.04 big M. I'm going to write that in fractional form. 0.40 moles of copper 1 chloride per 1 liter of solution. So I've taken this number here, and I've written it out in fractional form. You with me so far? I've taken my number and I've written it in fractional form. Okay, this is 500 milliliters, whereas this is a liter. So can I convert this to liters first? How many liters is 500 milliliters? So I move the decimal back. How many? 1, 2, 3. So it's dividing by 1,000, right? I'll write that up here if you forgot. 500 milliliters times 1 liter over 1,000 milliliters. Milliliters cancel, so that's divided by 1,000, so that's 0.5 liters. So I'm going to take my molarity, which is here, times my volume, which I just calculated by using dimensional analysis, to be 0.5 liters. What unit cancels? Liters cancel, and I have 0.4 times 0.5, 0.02 moles of copper 1 chloride. Okay, that's just helping you get set up with what is your given really giving you. So this is a given. All right, now let's finish reading the problem. If blah 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 chloride is reacting completely, how much copper will precipitate? That's much as grams, right? Grams of copper will precipitate from the reaction. Let's talk now. If I have to go to grams of copper, but I'm starting with moles of copper 1 chloride. Let's talk through this first. I'm starting here. What do I have to do first? I have my reaction, right? I have to convert from who to who. So copper chloride to just copper. What's that relationship? 2 moles to 2 moles, right? So I take my moles, I put my mole ratio, 2 moles of copper over 2 moles of copper copper 1 chloride. Now I'm in moles of copper. Okay, if I'm in moles of copper, what's my next step if my final destination is grams? Use molar mass to get from moles to grams. All right, I'm gonna have to pick up this on Wednesday. Here's what I want from you though. Look at your sheet. You see it says you try lecture practice. You try lecture practice. You are going to do 1 through 4. You're going to set them all up. If you feel like, oh my gosh, I don't know what I'm doing, you can rewatch the video, but you will do 1 through 4. And just baby start problem set 12. Baby start problem set 12. You notice that you're doing the 2 false, okay? So 1 through 4. Even if you don't know how to do the molarity ones, because I gotta finish those up, I want you to start them. And please, if you have your laptops off already, you can put them up, that'd be great. Yours are leaving in 1 minute. If you have some more stuff, I'm gonna write your name on it, so I'll give you a little cash, a little mole money. Mole money? Mole problem. Oh. I can print it right now. Hold on. What's your class? Okay.
Yeah.
Thanks. Oh my gosh. Is that okay? Is that too loud? told you which laptop said?
Some of the rooms are blue.
There's a box. There's a box. That's all. Oh, it's right here by the laptop.
My dad's a chef. He works at Gordon Food Service, and right now he